Okay, so this video is on writing and solving related rates problems. Related rates, which you guys are going to be working on in class, are problems where we look at a problem where different variables are changing over time, and we work through the problem by taking derivatives with respect to time instead of with respect to x. So we'll go ahead and get started with these. Okay, so kind of the way that you need to work on solving a related rates problem is you need to understand the problem, draw a diagram to represent the situation. Usually these diagrams are going to be some sort of geometry formula. Often it's going to be Pythagorean theorem, or a volume formula, or a surface area formula, but you need to kind of make a picture so you can see what formula you're going to be using. You're going to fill in the unknowns and givens in the problem. Rates will be with respect to time, so they'll always have a time unit involved. Another thing you should probably make note of is the numerator should kind of match what you're taking the derivative of. So like cubic centimeters is a volume. So this is a change in volume with respect to time. This could be like a height, a radius. These will definitely be derivatives. And then you're going to write an equation that relates your variables together. Don't worry about the rates. Those will be used after you complete the derivatives. Then you're going to take the derivative with all variables with respect to time, and you're going to solve for the variable you want to know about. So we're going to do a couple problems on today's lesson and a couple more, maybe more complicated ones on tomorrow's lesson, and you guys will get plenty of practice in class working on related rates. Okay, so for this first one, a pebble is dropped in a calm pond, causing ripples to form concentric circles. The radius of the outer circles is increasing at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So just to kind of draw a diagram, it's saying basically I drop this pebble in the pond and we get these. That is not a circle. I'm going to try and draw some circles again. You drop a pebble in the pond and we get a circle, and then it spreads and you get another circle. I don't know why it keeps doing that. Spread and you get another circle. It does not want me to draw the circles on this one. I'm not sure what's going on there. But basically we're going to be trying to find how fast the area is changing of these circles. So one, let's write down kind of what we know. We know the radius is going to be 4 feet. We know that the rate the area is increasing, or the radius is increasing, is 1 foot per second. So this is a dr dt. It's the radius and time. So it's 1 foot per second. Notice there's a time unit there. We don't know the area. And I definitely don't know dA dt. Okay, so once we have our variables identified and our givens, we're going to be looking for this. So what I'm going to do is set up a formula that relates the area and the radius. So the area of a circle is pi r squared. And what you're going to do is then take the derivative of this with respect to time. So the derivative of area with respect to time is dA dt. Pi is not a variable, so this is just a constant. So the area, the derivative of this side will just be 2 pi r and dr dt. Notice when we do this, we have to do multiple implicit differentiations. Our time variable doesn't match either the area or the radius. Okay, so we're going to kind of plug in what we know now. We are looking for dA dt. We know it's 2 pi. Our radius is 4, and dr dt is 1 foot per second. So I guess if I could write in the units, you can see how the units match up. So in this one, it would be 8 pi feet squared per second. And that makes sense because it is a rate of change of the area, and area is in feet squared. And time is in seconds. So the dA dt is 8 pi feet squared per second. Okay, so for this last problem on this video, air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. So that's going to be a volume with respect to time. So it's going to be a dV dt, just so we're aware. Find the rate at which the radius is changing when the radius is 2 feet. So basically what's happening is you have this balloon, I don't know why this is not, and it's a sphere, and so we're going to be working through, it's a terrible drawing of the sphere, but it'll have to work. What's happening when the radius is 2 feet. And I want to know how fast is the radius changing. So let's just kind of list our unknowns and our knowns. We know dv dt is 4.5 feet cubed per minute. I know the radius is going to be 2 feet, and dr dt is what I'm looking for. So when you kind of think through this, you're thinking about, okay, they gave me dv dt, they're looking for dr dt. What formula could I use that relates the volume and the radius? So for a sphere, the volume is 4/3 pi r cubed. So we're going to take the derivative of this with respect to time. And so on the left side, we're going to end up with dv dt. And on this side, we're going to bring down the 3. So we end up with 4 pi r squared and dr dt. And we're going to be solving this for dr dt. So I have 4.5 feet cubed per minute equals 4 pi. The radius here is 2 squared, and then dr dt. So I have 4.5 equals 16 pi dr dt. So I'm going to divide both sides by 16 pi, and I'm going to type this in the calculator. And when I do that, just make sure that 16 pi is in its own set of parentheses. Okay, so I typed that in the calculator, and when I did, dr dt was equal to 0.09